First of all, just want to say hello to everyone and really thank you, Steve, for this opportunity to give two lectures in your course. I think your students recognize that this course is a very unique course that summarizes decades of groundbreaking research by you, your colleagues, and your students. And it was really exciting to be part of this research 20 years ago. And I think it was a pivotal moment for development of medial representations when I joined your group, and it's just great to be back. And all right, also would like to acknowledge my colleagues at Penn who have been instrumental to a lot of the work I'll be presenting about continuous medial representations. And just a little bit about me. So I defended my PhD at UNC in 2003 with Steve as my advisor. Here's a little picture I found with Steve, myself, and my late father from the time of my graduation. And I've been at Penn since 2003. I started there with Jim G as a postdoc and kind of moved up the ladder since then. So right now I'm professor of radiology, and I'm also co-direct the neuroimaging core at our Alzheimer's disease research center. So as I've kind of been doing this, my work has moved more towards applications, and particularly applications to neurodegenerative disease research and development of biomarkers for Alzheimer's disease. A lot of what my group does right now is working with ex vivo brain imaging, with high resolution ex vivo MRI and histology of the human brain. But I'm still very much interested in shape-based image analysis techniques, and in particular in skeletal and medial representations. So what I'll talk about today is give a brief review of just medial geometry and principles, and I'll really just skip through this very quickly because this was covered in the last few lectures, but it's never hurts to just kind of redefine the notation that I'll be using. The bulk of what I'll talk about are two classes of what I call CMREP, or continuous medial representation approaches. The first type of approach is called inverse skeletonization, and the idea is that we start by parametrizing the skeleton of an object, or a representation of a skeleton of an object, and then we kind of reverse the grass-fire transform to generate a boundary in a parametric way. And then the second class of approaches I'll talk about is kind of the opposite approach, where we start by parametrizing the boundary, but we impose constraints on boundary points so that that boundary corresponds to a medial axis of a certain structure. And of course, I'll go through details of both of these approaches as we get into the slides. And Steve also asked me to talk about some of the applications of medial representations, and I also included a couple of just more what I call medial tools in general, some of the things that leverage some of the ideas of medial representations without necessarily using them. And those will roughly fall in the areas of heart valve segmentation and morphometry, which is the work headed by my colleague, Assistant Professor Allison Pouch at Penn. A little bit of our work on intersubject normalization using medial representations, and I'll also talk a bit about atlas building and longitudinal morphometry. So please do interrupt me as I speak. If you have questions, I'll try to keep an eye on the chat as well. But you can just don't feel bad to speak up and ask questions. So I'll start with a little bit of motive. Oops, trying to hide all my things that just showed up on my screen. I'll start with a little bit of motivation for medial representations in general. The way I see it, I'm sure you have also seen a lot of motivation already in this course. But for me, a major motivation is just the prevalence of sheet-like structures in anatomy. So some of the examples I just show here. We have here on the left white matter tracts that tend to organize themselves into sheets of axons. We have some brain structures. This is a mouse hippocampus. This is histology slide of a human cortex. And again, we see this very characteristic sheet-like organization. Here we have a model of the myocardium. Here we have heart valves in an ultrasound image. Again and again, we encounter this organization of tissue into sheets. And geometric representations that are explicitly connected to the sheet-like geometry have to have certain advantages over more general representations, general boundary mesh. And in fact, they give us access to features such as thickness, features such as branching, and these are the same motivations that I learned from Steve when I was taking my first courses at UNC about the use of medial representations. I don't think any of that has changed. So I've showed some examples in my work of where medial representations in particular have been useful. One major use is thickness measurements. Again, for sheet-like structures, thickness is just a natural feature to describe them. In the brain, for any cortical region, the measurement that people tend to report is thickness. It's a lot more relevant than, for example, volume, in part because specific regions in the brain are hard to define. Their boundaries are very hard to define. They're based on site architectural differences. Even neuroanatomists sometimes cannot agree, within a centimeter of each other on boundaries. And volume very much depends on where you place boundaries, whereas thickness is much more robust. You can move a boundary half a centimeter left or right, and still the average thickness might only change by a few percent. And that's really, like, in a practical sense, working with neurologists and neuroscientists, thickness is just much more relevant than volume. Another area where medial representations have proven useful is for normalization. And again, this is something that Steve recognized many years ago, is that the medial axis provides a very intuitive coordinate system for the interior of an object. And we can use this coordinate system to match data between different sheet-like structures in a much better way than if you apply deformable registration to these structures with just standard smoothness constraints or standard diffeomorphic techniques like LDDMM, because this coordinate system, it maps proportional distances to proportional distances, in particular distance between the boundary and the skeleton to distance between boundary and the skeleton. And so when you describe a normalization procedure, you can give some intuition behind why this is matching to this, as opposed to just, oh, this is what the algorithm generated, because that's minimized some smoothness regularization term. Segmentation, of course, is another area where medial representations are a powerful tool, because when we want to segment sheet-like structures, it makes sense to impose priors that also recognize that sheet-like geometry. And so early on, we have used some of the earliest continuous medial representation work for myocardium segmentation, again, as a prior to sort of help a machine learning-based method differentiate myocardium from similar looking tissue while respecting its thin sheet-like structure. And of course, shape analysis. And I didn't even put any bullet points under shape analysis because that's such a major part of this course. you know, I just don't think I can say anything to add to what you have already learned or will be learning. So, very quickly, just remind you of medial axis and medial scaffolds. So just very informally, a medial axis is what you get if you start thinning an object uniformly until it collapses to an infinitely thin set of curves or set of surfaces in 3 dimensions. Another way to describe this using the grass fire transform, and examples of medial axis in 2D and 3D shown here. The definition that I will be referring to define this concept of inverse skeletonization is from Blum, from the original Blum paper, that a ball, we first define a maximal inscribed ball. So a ball is called a maximal inscribed ball in S if so S is here an object or shape. If B is inscribed in S, and there's no larger ball that's inscribed in S that contains B. So basically, it's a ball that is, you can't make it any larger and still contain it inside of the object. And the medial axis is defined as a set of all centers of the maximum inscribed balls inside of an object. And in fact, the medial axis maps each point on the boundary of the object to a center of this maximal inscribed ball. Again, I think you have seen this definition. And going back to this thickness, one attractive property of the Blum medial axis is that it gives you a robust and I would say usually biologically meaningful definition of local thickness. So people like to measure thickness, and there are many techniques for measuring thickness, but sometimes people would like to just point along the normal and see what happens, you know, how long you go until you hit the other side of the boundary. And when you're in a situation on the left, great, it makes tons of sense. But you can also end up with situations like I've shown here, where shooting along the normal until you hit the other side of the boundary gives you a very meaningless definition of thickness. Whereas if you define thickness as a distance from the boundary to the closest point on the medial axis, then that's a well-formed definition. Even though, you know, sometimes it is perhaps a little bit arbitrary at the tips of the figure, but it's still mathematically always well-defined. Of course, there are other definitions based on differential equations, like Laplace equation, that also are meaningful and intuitive. So it's not the only meaningful definition of thickness. So a little bit about the properties of medial axis and medial scaffolds. Again, you've learned about these different kinds of points. Majority of points correspond to a maximal inscribed ball that is bitangent to the boundary. But you also have a single tangency with a higher order of contact that corresponds to the endpoints of these medial curves or to the free edges of the medial surfaces. And then we have branching points, which have generically will have a third order contact. I mean, not a third order contact at 3 boundary points. You also have special points that you've seen in the Giblin and Kimia chapters that you've read. Of course, points that correspond to the this end point of a fin, which is a junction of a branch curve and a free edge curve. You also can have a branch intersection, which is not shown here, that also occur generically, and will not be focusing on them too much. And another thing that you have also heard about already in this course is this problem that people frequently bring up when you talk about using skeletons or medial representations, is that the skeleton is unstable, that if you make a small perturbation to the boundary of an object, then you can create branches in the skeleton, And even though there are many pruning algorithms that people have proposed for getting rid of what you call spurious branches, it's very hard to do this with any kind of robust guarantees, and you still can end up with, no matter how much you prune, it's very hard to guarantee consistent branching structure or even very similar shapes. So if we want to do statistical analysis using features derived from the medial axis, it's difficult because it's very similar objects sampled from the same population of objects will almost certainly have very different branching configurations. So for the purposes of shape analysis or normalization or segmentation priors, et cetera, this direct skeletonization, starting with a segmentation of an object of interest, skeletonizing it, and then extracting features from it, or imposing some kind of constraints on it, is very, very difficult to work with. And so the opposite approach that was introduced in the MREP papers by Steve in the late 90s is to invert this and start with a parametrized or synthetic medial model that you can deform and that you can fit to your object of interest. You're not going to be able to fit it perfectly because the object of interest has its given skeleton, but you can, in many cases, fit it very closely. You might fit it with 95% dice overlap or something like that, while preserving the medial structures. So for example, here on the left, we have this blue object. This is a segmentation of the corpus callosum, a white matter structure in the brain. It has its branchy, bushy skeleton that you see down here. But here is a medial model that consists of a single surface, single parametric surface, corresponding boundary that if we were to skeletonize this boundary, we would get back as the skeleton this surface with its radius function. And this boundary model closely fits the object of interest, again, with 90-some% overlap. So considering that our segmentations of the objects of interest are not perfect to begin with, if we can fit these segmentations close enough with a predefined medial model, then we can do statistics based on skeletons and based on thickness maps that we get out of skeletons and so on. And so essentially this becomes an optimization problem where the tools that we need is a way to go from a parametric representation of the synthetic medial axis to a boundary representation. We want to be able to do this in an efficient way because we have to do this at every step of the optimization procedure. And then we have to have some way of comparing our boundary model to the object of interest, and then, of course, taking gradients. These days, nobody takes gradients because PyTorch takes gradients for us, but in my days, we had to calculate all these on a back of paper, and it took enormous amounts of time to compute these gradients. So I think I've mentioned most of these papers from Blum, Giblin Leukemia, Pfizer, and Damon. These are some of the key papers in deformable medial modeling. And now I'll start talking about in particular, the continuous medial representation. See if there are any questions so far. All right, so so this figure is I think still from my thesis. This is kind of the earliest concept of continuous medial representation, where we would define a synthetic medial axis as some kind of a spline. The red points here are control points. We would assign every control point also a radius value. So a control point had an X and a Y and an R. And then we would use the spline functions to interpolate the medial curve and also interpolate this continuum of circles, and then compute the envelope of this continuum or family of circles which would form the boundary of the object. And then we would deform this by moving the control points and changing the radii of control points. We can deform this synthetic model and fit it to binary segmentations of structures. Oops. In 2D, this is pretty straightforward. You don't have to think much about extending this even to branching structures in 2D, but in 3D it gets more complicated, substantially more complicated. So in 3D, we would also have a synthetic medial scaffold. Here, the control points are not shown, but they're always there. There's always some kind of a set of coefficients that determines the shape of this medial scaffold. And again, painted on this medial scaffold is a function or a scalar field, call it the radius scalar field. And just like in the picture above, we interpolate and generate a envelope surface or envelope curve. Down here, we obtain a continuous boundary as the envelope of this continuum of spheres that we get from these two inputs. So it turns out that envelope of a family of spheres or circles has a very nice, elegant formula for it. So first, all we have to do is give it implicit definition for a sphere. So point Y somewhere in space belongs to a sphere centered at U, centered at X of U. If its distance to X of U is equal to the radius at U. So just to explain again what I'm saying here is we start with a parametric surface or curve X of U, and we have this scalar function R of U, that's the radius. U here is used to parameterize this curve or surface. And so then we end up with a function that depends on Y, which is a point somewhere in space, and on U, which is the coordinate used to parameterize the surface. And at the envelope, this function S has value 0. And you can then argue that not only on the envelope, the S has to be 0, so the point has to be distance R from a center of its circle, but also the derivative with respect to U of S has to be 0. So if you move a little bit with respect to U, oops, you also have corresponding point on the envelope that's just a little bit away from Y. And this set of equations can be reformulated to give you a pair of points Y corresponding to every U. So these pair of points, remember the generic case, or the most common case, is that a maximum ascribed disk or sphere is bitangent to the boundary. So these points are going to be the opposite ends of the medial axis, and they're going to be given by this expression X U plus R of U, and then multiplied by this vector expression, which says, so this vector from X to Y, we can compose it into a portion that is normal to the surface and a portion that is parallel to the tangent plane of the surface. The portion that is parallel to the tangent plane of the surface is this grad R, and that's the vector describing the change in the scalar field R with respect to the parameter U. And the remaining part is the normal component. So you get this by just working out this pair of equations. So this grad R is a very important object in working with Blum medial axes and with medial representations based on them. So I just wanted to put a little bit behind what grad R is. So in general, when we talk about the gradient of a scalar field on a manifold, it is defined in terms of the first fundamental form, So first fundamental form is a matrix of dx by du1 and dx by du2. They're corresponding dot products. This actually here with the indices in a superscript is the contravariant metric tensor. So it's the inverse of the first fundamental form. And then we have here the tangent directions corresponding to the components of u, and then the change in function f, of course, with respect to the components of u. The main point to take out of this is that it's a non-linear expression with respect to x of u. So the grad r is not just ru, rv. No, it's ru, rv, but it also involves a rational expression in the first derivatives of x, which is of the second order. Okay, so going back to this expression, so here we have a way to describe the boundary, this envelope, as a function of x and r. All we have to have is x is a function of u, r is a function of u, and then a bunch of these first derivative properties. So the grad r on the manifold, the normal, and the square root that it involves is the norm of grad r. So we should be able to calculate it in a straightforward way and generate boundary surfaces to correspond to medial surfaces and radius fields. The problem is that if you just put an arbitrary function x and arbitrary function r in this, you'll have two problems. First of all, y1 and y2 are going to be disjoint surfaces. And that's because we want them to come, if we want them to come together along the edge of this manifold x, y1 has to equal y2. And for y1 to equal y2, there's a certain constraint that x and r have to satisfy along this edge that arbitrary surfaces will not satisfy. The other problem is that if you put in arbitrary x and r, it's very likely that you'll end up with y that has all kinds of singularities, folds and stuff in it. Again, because this has to do with the curvature of x and the rate of change of r, and if x curves too fast or r changes too fast, y is likely to cross itself. So it's not so simple. We cannot just write down this expression and go home. We have to make sure that whatever the inputs x and r we put in will not create these two kinds of situations. And so in my work, I've mostly focused on the first problem, making sure that y1 and y2 come together. I have mostly punted on the other non-equality constraints that are required to prevent self-crossings and stuff. That is to say that you can always come up with various penalty terms that you can throw into the optimization that will most likely prevent these kinds of second problems. But the first problem,
just the S sub rad that Damon produced is intended to handle that other problem. I mean, go on.
Exactly, and that's so along the edges, if we work out what does it take for y1 to match y2, then essentially it just says, if you look at what's different between y1 and y2 is that you have a minus here and you have a plus here. And so we want whatever is being subtracted here and added here to go to 0, which is to say we need the norm of grad r to be equal to 1. And so that's really the constraint. That along the edges, we need grad r to equal to 1. Again, this is a nonlinear expression involving x, r, and their first derivatives. And similarly, if we look at the seam curves, we have a set of related constraints, also involving grad of R. But now what's grad R has to equal to has to do with the angle between the angle at which the medial surfaces come together. So the dot product of the normals of the two adjacent surfaces. But it's a similar problem that along these curves here and here in 3D, we have to satisfy these equality constraints. This is the fundamental reason why 3D is so much harder than 2D. In 2D, these constraints only apply at a set of points, so it's a finite number of constraints. In 3D, they apply along a set of curves, so it's an infinite number of constraints that have to be satisfied on these surfaces that will typically be parametrized using a finite number of coefficients. So these constraints are going to complicate shape analysis. Again, just repeating here, in 3D, a nonlinear equality constraint must hold at an infinite number of points, but the number of parameters of the model is finite. And of course, even if we were able to somehow get two models, A and B, to satisfy these constraints, any kind of linear operations involving A and B, like A plus B over 2, will almost certainly break that constraint because of the nonlinearity of the constraint. Right? And so if we want to do any kind of shape statistics, compute means, do PCA, etc., it becomes meaningless under these constraints. So we need some way of generating models that satisfy the constraints and doing shape statistics with models that satisfy these constraints. And one way to do this is if we can find some kind of a map, a one-to-one and onto map between a space of parameters, oops, sorry about that, a space of parameters and the space of models that satisfy these constraints. So if the parameter space was a vector space where we can average A and B and get a new set of parameters C, and we have this bijective map that will map C onto the manifold of all the models that satisfy this set of equality constraints, then we can start to do statistics. So for example, we can move, we can interpolate between A and B, etc. Now, there are a lot of analogies for this kind of situation that you might have seen or will probably see in various courses related to image analysis. So one of these is rotation matrices. So if you think of a rotation matrix, it's in 3D, it's a rotation matrix is a 3x3 matrix that's orthonormal. So its rows are orthogonal to each other, and dot product of each row with itself is 1. So it's a special kind of manifold of 3x3 matrices that satisfy these conditions. It has a name, SO3. And if you take two rotation matrices and you average them, just average their coefficients, it will no longer be an orthonormal matrix. It will no longer be a rotation matrix. However, we have different ways in which we can parameterize rotation matrices using a vector space. So for example, one of these is called the exponent map, where we can take a three-dimensional vector, place it into this skew-symmetric matrix SV, and then exponentiate this skew-symmetric matrix SV. And by exponentiating it, we will get a rotation matrix. So this is a map that takes every set of three numbers, every point in three-dimensional Euclidean space, and maps it onto a rotation matrix with some degeneracies around 0, but in most of the space. This map behaves very well. Oops. Another example that might also be familiar to you is in diffeomorphic papers. So LDDMM, one of the most written about and well-known methods for image registration. Again, we have this situation where we would like to model registration as a diffeomorphic transformation, a transformation that that has a no foldings and has a greater than zero Jacobian everywhere, because that kind of deformation imposes correspondence between objects. But if you take two diffeomorphic transformations and average them, you can easily get a non-diffeomorphic transformation. But there exists this mapping, this other parameter space. This time it's a space of smooth velocity fields that are parameterized by position as well as time. And using this ordinary differential equation called the flow equation, we can define diffeomorphism phi as a solution at the time one of this flow equation. So this differential equation acts as a kind of a black box that takes as an input the smooth velocity field, which we can take two smooth velocity fields, average them, and we still get a smooth velocity field. And you put it through this equation, and out you get a diffeomorphism that lies on this manifold of diffeomorphisms. So, here's an equation of differential equation being used to map from a parameter space to a constrained space. So the first class of continuous MREP approaches try to play with the same idea. Can we find some kind of a differential equation that will allow us to map from a unconstrained or less constrained parameter space into the space of medial models that satisfy these grad R constraints? For now, I'm just going to focus on this grad R equals 1 constraint. So where our surface just consists of a single, or where our medial model consists of just a single surface. So the setup here is that we're going to start with some kind of surface X, and we'll paint on it a scalar field rho, some function for which we might have some inequality constraints, but not equality constraints. And we'll solve a differential equation, and hopefully we'll get out an R that satisfies the constraint that we have before, the grad R equals 1. And the reason this PDE came to mind is because we have this situation where a constraint holds along the boundary of a surface. And of course, when we study differential equations, partial differential equations in particular, we always think about boundary conditions. So the idea was like, well, can we just rephrase this problem of satisfying this constraint as solving a differential equation with a certain boundary condition? But the question was, what kind of differential equation? So it was clear that it had what the boundary condition had to be, because we know from the medial geometry what we're trying to satisfy. But what wasn't clear, what is the operator that should be applied to the function R in order to get a well-behaved solution. So actually, the first thing I tried was a Laplace equation, or Laplace-Beltrami. So, sorry, Laplace equation. Sorry. It's the Laplace-Beltrami operator, but I think it's still called Laplace equation. And basically, second order operator here. And it worked, but it had a limitation, and it had a limitation that this boundary condition is still nonlinear, and solving a differential equation with a nonlinear boundary condition, you cannot solve it in one pass. You actually have to solve numerically, you have to solve a sequence of differential equations with linear boundary conditions. So a little bit later, around 2008, came up with the idea of using a fourth order operator, so which is called a biharmonic equation. This biharmonic equation is also is involved in defining thin plate splines, which is one of the methods very early on used in shape analysis and registration. So it's basically the Laplace operator or Laplace-Beltrami operator applied twice. So Laplace-Beltrami here has to do with when it's on a manifold, we call it the Laplace-Beltrami operator. In Rn, we would just call it the Laplace operator. So it's a fourth order equation, but it basically means we're applying the Laplace-Beltrami operator twice. And here you can see the nitty-gritty of what it looks like, the Laplace-Beltrami operator. Again, it involves first and second fundamental form. So the first fundamental form is here, and then it's being differentiated. But there are efficient ways to compute it on digitized surfaces. So why this fourth order equation? Why not? What's the advantage? And the advantage of the fourth order equation is that it requires two sets of boundary conditions. So not one, but two. And typically it's one of them is a Dirichlet boundary condition that the function that you're trying to find, the unknown function, is equal to some given function along the boundary of your domain. And the second boundary condition is the von Neumann boundary condition, that the derivative of your function in a normal direction to this edge is also given by something. So typically you would just have some function f1 here and some function f2 over here, and then it's a well-posed equation. And what's neat here is that, okay, we have this nonlinear condition grad r equals 1 that we want to satisfy. But if we prescribe r along the edge here, so r here is prescribed as r0, then we can figure out based on just the derivative of r0, what the derivative of r in the orthogonal direction should be. So it's just this. Okay, so basically, if we know that r is equal to r0 along this curve, I'm sorry, and if we know that grad r is equal to 1 along this curve, we can just write down an expression for the von Neumann boundary condition using this square root that just involves the derivatives of r0. So it becomes
Paul, can
linear.
I make something clear, please? R sub 0 is nevertheless a function of position on that boundary. It's not constant, right?
It's not a constant. It is a function of the position on the boundary. Absolutely. But when we're modeling this, when we discretize this, we can prescribe r0 at the boundary nodes and interpolate it along the curve, which is what basically is done. But the upshot here is that it becomes a linear problem. It can actually be solved as two sparse matrix inversions. So this is kind of the flow of this method. We start with now a set of parameters. X is somehow parametrized, some parametric surface S. Rho is a parametric function, and R0 is prescribed, but just at the boundary. Some function prescribed at the boundary. We solve this differential equation, and we get an R that now satisfies grad R equals to 1 everywhere along the curve. Y is just computed as formulas that I showed you in the beginning. And now we can just match this to an object of interest.
So let me make one thing clear. Could you go back to the 2 slides?
Mhm.
One more slide back. Okay, so when you're solving that equation, what this yields is an R function. What is the behavior? What is rho?
So rho is something that you prescribe. So it needs to be smooth. It needs to be bounded. You can certainly come up with rho that will give you bad solutions, but the idea is really this, right? So here we just kind of associated every control point with an R value and interpolate it. Well, now we're going to associate it with a rho value and interpolate it. And then we'll solve the differential equation and it will give us something. I cannot a priori say what rho should be, but in an optimization sense, I can start with rho being 0 everywhere and then optimize over X and rho until I fit the object to something useful. So it's, it's just like, velocity field in LDDMM, although there has a much clearer physical meaning. But I mean, it's also, we know what rho is. It's the Laplacian of the Laplacian of R. So it does have some physical meaning. So a couple things. So I think I already talked about why biharmonic equation, why not just Laplace's equation. That had to do with getting rid of the nonlinearity. Some of you might have caught a little thing here. Why do I have R squared here and not just R? So I kind of played a little trick here. I had L of R, and all of a sudden here I have R squared here. So actually I was giving a talk, a job talk a few years ago, and somebody asked me that question. I was completely flustered because I forgot. So this time I went back to the paper and I tried to remind myself why R squared. So there are 2 reasons. So one thing is, if you work it out for an ellipsoid, if you just take an ellipsoid in XY plane, I mean, an ellipsoid with a major axis parallel to the XY plane, and it's kind of a very characteristic object with a single sheet medial axis. So it turns out that for an ellipsoid, the biharmonic operator applied to R squared is equal to 0, but that's not the case for R. So that was one aspect, and more generally, if you formulate the equation with R squared and you prescribe R0 to be equal to 0 along the boundary of the domain, then the solution will be R equals to 0. But again, this is not the case for R. So we can just think of this equation as being in terms of some other function phi, which is equal to R squared. It doesn't really change anything, but it makes some things a little more attractive. In particular, starting with 0 with rho equals 0 kind of makes sense in this equation. A little bit about practicalities. So how do we actually go from all these equations to a practical, usable, deformable modeling method? So the first thing is how do we represent these surfaces in 3D? And so at the beginning, used 2-dimensional splines, B-splines and stuff like that. But it turned out that it's much more convenient to work with triangular subdivision surfaces. So loop subdivision surfaces are, it's a very early computer graphics method, but it's a type of a triangular spline. And basically you define a grid, a triangle grid, and then there are rules that tell you how to interpolate this grid further and further. And it's convenient because you can have more control over the shape of your medial surface. If you use a spline, which is like a product of a spline in U1 and a spline in U2, it's going to have corners, whereas your objects a lot of times don't have 4 corners. And so working with triangular surfaces just kind of simplified a lot of things. Another thing you get with loop subdivision surfaces, it doesn't only tell you where the points are as you subdivide, it also tells you the tangent plane. So there are rules to generate vectors in the tangent plane and the normal vector, and it always involves just a one ring of vertices around the vertex you're interested in. And they're all very simple linear functions of these neighbors. And so, there's natural kind of multi-resolution properties to these loop subdivisions surfaces. You can fit at a low resolution and keep increasing the resolution and adjusting your fit. The operator itself, the Laplace-Beltrami operator, there's a lot of literature on how to approximate it well on a triangular mesh. It kind of, the quality of approximation depends on the quality of the mesh. So if you have meshes with very long and skinny triangles, you will have a poor quality approximation. So the approximation we use is it's called a Cotan formula. It basically to approximate the Laplace-Beltrami operator at a node xi, we use an expression that looks at all the neighboring nodes and also the cotangents of these wing angles, alpha and beta. And to deal with the quality of the triangulation, one method that can be used is to do some edge flipping, like do a kind of intrinsic Delaunay triangulation of your mesh as you're computing this, and that improves the accuracy of the LBO approximation. And ultimately, when you do this, so for example, if you look at this operator is some expression involving geometry here, but it's linear in the f function over which we're solving the equation. So it all just ends up a very large sparse, not very large, it just becomes a sparse matrix that an expression ax equals b, where a is a sparse matrix, x is your unknown function, and b is a vector. A and b are nonlinear in x, but it's linear in the unknown function. One practicality is building these templates, right? So, here I showed a sphere, but in real life, we need to actually build models that we can then deform to real objects. And this has been kind of a headache for all the time that I've been working with these models. We've tried a bunch of different stuff, but recently my colleague Alison Pouch, whose work I'll keep showing as we go through the slides, she's been leading up the development of a plugin for Slicer that does this template building. So, and the way you do this is you input some characteristic model, or maybe it's a template that you've built from a bunch of binary segmentations, just like using diffeomorphic techniques. You skeletonize this model, and then you go in and you place points on the model. So these are your medial points, and then you organize them into triangles, and this gives you some kind of control over the quality of the triangles. And then it'll you can generate a medial model in the right format. It can apply subdivision. It can inflate it as well to give you a boundary model. So it's a nice tool. It's still in development, but Alison's working on a paper describing it, and it should be coming out pretty soon. And it also works for branching models. I'll get later, probably next lecture, I'll get to branching medial models, but this tool does support branching models as well. part of what you can do is you can label different points of different types. So these are edge points in red and internal points in blue. So we have a way of generating these models. We have now a way of going from parameters to medial models to satisfy our equality constraints. And we have a way of inverse skeletonization. A couple of things I still haven't talked about are, to make this work in practice, we need additional penalty terms. So even though the grad R constraint is satisfied, we still need to make sure that the model is non-folding. We need to make sure that the solution is positive. So even just as simple as that, it's very easy to come up with the rows that will give you a negative R. And so, so we need to, or maybe no, because we solve for, forget that, the positive R, it does not apply in this PDE case, because the solution is R squares. We just take a square root. Square root of a positive number is a positive number. So that comes up in something else I'll show later. Non-folding is important, and the way that we impose non-folding is that we look at the Jacobians of the little wedges that are formed by the spokes and make sure that those Jacobians are non-negative. So it's a kind of inequality constraint that we apply at every triangle on this shape. So it adds to the cost of computation. Anytime you add penalties, it's always mucks with your optimization. So that's kind of the unattractive aspect of this. Sometimes for some problems, we also have to add some kind of a kludgy diffeomorphism term, which is not to say that we do some kind of LDDMM here. It's literally just like checking for self-intersections. So for like a model not coming around and crossing itself. And that's pretty expensive. The other thing is, how do we match objects of interest? So in my experience, boundary matching just doesn't work well. It does not work well because you have to initialize your model very closely to the target object for the boundary distance-based metrics to work well. Otherwise, it loves to have two sides of the boundary collapse to one side of the boundary, or just not stretch into the object, etc. So the beauty of the medial models is that you can do volume-based similarity metrics. Because the medial model gives you access to the entire space between the boundary and the medial surface, it's very easy to compute overlap between the binary segmentation of an object and this medial model. So you can do dice overlap. That's something that, you know, with simple like boundary models, it's not trivial to compute dice overlap between an interior of a model and an object of interest. But with the coordinate system that a medial representation gives you, it's linear in just the number of nodes that you have. So finally, a movie just showing you, oh, the movie's not playing. It's playing in green for some reason. Oh, there it goes. Okay, now it works. So on the left, we have the X and the rho shown. On the right, we have the solution of the differential equation, X and R. And at the bottom, you have the fit to the target object. There we go. So really this kind of opens the door to doing a lot of things that we wanted to do to begin with, like, you know, finding average shapes and doing PCA, et cetera, et cetera. So some examples of PCA, and shows here that as you go along one PCA mode, you can easily break inequality constraints. So yeah, so as I said, mostly punted on inequality constraints, where you know, it is important to take them more seriously, like in Jim Damon's work. So it's 4:30. I wanted to just make sure that I answer some questions if there are any before I go into some applications and then the other model.
Can you say some more what you mean by statistics on? Yeah, could you say more about what you mean by statistics?
Yeah, so statistics here, what I mean is, you know, it's kind of descriptive statistics. So let's say we fitted a bunch of models to a bunch of binary segmentations. So these are hippocampal shapes, and these are fitted hippocampal shapes. You know, what's the average shape? So if we just average the parameters, the rows, and average the manifolds, and then solve the differential equation, we can get something that, you know, a valid shape. Now, it is not the mean in the same sense like a Fréchet mean. So if we wanted to do a Fréchet mean, something that sort of minimizes on the constrained manifold the distance to all of the points, then we would have to do optimization. We can't just average a bunch of stuff and you know, inverse skeletonize.
So you have no explicit distance function, right?
Yeah, so it's basically averaging in the parameter domain, and yeah, so it is kind of limited in that sense. So we're basically saying no, we have a bunch of points in this parameter space, we find their average and then map it onto the manifold. Same thing with you know, PCA, where the PCA I showed is doing PCA in a parameter space and then mapping it onto the manifold. Now defining a distance function, you know, I think it should be possible to define a distance function, but I have not looked at that. I have not looked at just kind of, yeah, just, you know, kind of stuff that people do with geodesic shooting for shape averaging and for statistics. I have not done that. But it could be a nice project for somebody in the class looking for a project right there. All right, should I just talk for another 10 minutes?
Yes.
Okay. So just show you a little bit of examples here. So this is from a paper around 2008 or so, where we fitted this to a bunch of white matter structures. So at the time, working on with Gary Zhang, who's now a professor at UCL, the inventor of the naughty technique, which is very widely used now for looking at diffusion of gray matter structures. But at the time, he was working on registration for diffusion data, and we worked together on this project for using medial representations as a way of normalizing data derived from diffusion imaging. And the first thing we had to do is just fit these white matter structures, and this is showing, just fairly complex geometrical objects being described by single surface PDE based medial representations and achieving a pretty good fit. So for example, I don't know why it says left hippocampus here. I guess I was patching together slides, but yeah, pretty good overlaps for these white matter structures. This is just a figure, but another way in which we used these representations was, as I mentioned before, for normalization. So in particular, again, this is two-dimensional corpus callosum, but the idea is, if you have rich intensity information, then deformable registration, image-based deformable registration is a good way to match corresponding locations, probably. But if the intensity is almost constant in a structure, like and the corpus callosum is just almost constant in intensity, if you look at it in a structural MRI scan, then deformable registration gives you kind of hard to predict deformations. So one part could kind of stretch out more, one part could stretch out less. Whereas with a medial representation, if you fit the medial representation to both structures, you can define correspondence based on position along the medial axis, as well as where you are between the medial axis and the surface.
So this is just using arc length along the medial axis to parameterize this, or fraction of the arc length from one end to the other.
Yeah. So this, go back to this white matter paper. We kind of combine some of these ideas. So what we did here, we took a bunch of diffusion MRI scans. We built a template. Here template using like tensor properties. So it was, the white matter here is not uniform. It has information at every voxel based on diffusion. And then in the template, we did fiber tractography, extracted some of the principal tracts. And then we fitted these CM reps to the principal tracts. They do have this nice sheet-like structure to them. And then we used the medial geometry as a way to organize group analysis. So, for example, these tracks, you can see them kind of going through here, but we can go sample along the medial spokes and condense information, maybe take average fractional isotropy or average mean diffusion along the spokes and summarize them onto the medial surface. So we can get kind of maps like these for different individuals. And then we can do statistics on the surface. So, from the point of view of visualization, it's nice because you actually, surface is a nice way to look at data. It also has some robustness to registration errors, because if you look at, if you analyze data along a skeleton, rather than along the boundary, even if your boundary is a little bit misregistered, chances are the skeleton is still inside of the object after registration. And so we've had this tract-specific analysis pipeline. I mean, it's still there. People can use, just kind of tool for white matter group analysis of features from the white matter. One attractive thing about this is because these are parametric surfaces, you can flatten everything out. You can look at statistical maps in this kind of two-dimensional flattened view. It's another study that was published using this in Alzheimer's disease, looking at differences between Alzheimer's and frontotemporal dementia in terms of white matter damage. Here's another pediatric study that used this approach. It hasn't caught on as much as we had hoped, but there were a few papers that use this technique. And I guess this maybe the last slide that I'll show is that the PDE model is kind of nice mathematically, but in practice, sometimes we cheat and we don't use it. For there are various reasons. Part of it is it's kind of slow having to solve this sparse linear system at every iteration of an optimization. As to the computation time, especially if you want a high resolution model, eventually computational cost ends up being pretty prohibitive. I mean, part of the problem with solving a PDE is that the solution depends on every input, right? It's a global dependency. So something happening at one end of the model affects the solution at another end of the model. Whereas, you know, without this PDE, you know, things stay more local, which can be also attractive for optimization. So sometimes in practice, what we'll do is model things in terms of R, but you know, the problem is, you know, at the ends we have this grad R condition, and so what we'll do is we'll add another penalty and say, okay, how different is grad R from 1? Penalize it for being too different, and then it's never going to be equal everywhere because, again, this constraint is if you have a parametric surface, you cannot satisfy it at every mesh point, but we can always like fake it out. We can basically take these two spokes and average their positions and call that the corresponding boundary point. Again, it's not very attractive mathematically, but it tends to work pretty well for practical purposes. And so that's kind of another flavor of CMREPs that we sometimes used. So call it brute force fix and just the additional penalty term. So one place where we used something like this was where we wanted to use this representation for guiding segmentation as a prior in segmentation. And so we actually created a branching model, again, by just kind of faking these constraints at branch points and fixing them in a similar way, and use it in conjunction with some machine learning. I think with support vector machines for intensity matching, and a medial prior for shape, and it worked nicely. Some mean shapes and mean thickness maps and diastolic and systolic that we got with this method, and then change over the cardiac cycle. Again, so just a lot of times for practical applications, you don't have to do the full PDE method, but the PDE method does work. Like I said, just a little slower. All right, so should I stop and
Yes,
on Tuesday?
yes, yeah. Could you stay on, Paul? And first of all, take questions right now, if there are any, and then we'll ask the class to leave, but you stay on for a minute for us to talk.
Okay.
Sorry, is there any software or library that you can generate these CMREPs?
Yeah, so there is a library. Actually, at the end of my slides, I have a link to it. I can bring it up right now. Let me just see. Can I get out of the presentation mode? I'll just jump ahead. So it's just in my GitHub and it's called CMREP. Now it is not. So this is it. It is not the most documented. It is also kind of complicated to build because it has a lot of dependencies. So different methods that I'll talk about next time, some of them have dependencies on like this IP-opt library. So it might be a little bit tricky to configure, but if you're willing to invest, you know, a little bit of time into getting it to work. Everything that I talked about is implemented in this code.
Okay, so we'll let the class leave, and Paul, you just discuss for a moment about the way forward.
Okay.
Uh, Okay, well, we have one student still on, but that's not a problem. Okay, the first of all, next time, if you run short, don't worry.
Okay.
I can pick up with stuff that I have.
Okay.
If you run long, and you want, to continue a little bit into the following class, that's okay with me. But anyway, I'm saying there's some flexibility there in regard to the time you take up.
Okay. Yeah, I think I don't think I'll need a whole 75 minutes for what I have left.
Okay, then we'll take questions, and then I can pick up with,
Okay.
I still have a bunch of stuff on the SREP side of things that I haven't yet covered.
Okay. I might take an hour, maybe, I mean, depends, but
That's fine, whatever.
I'm not gonna
All I'm
run
saying
into
is whatever
it.
you take, and that's fine.
Okay, great.
Thank you for this, this has been for me enjoyable, and I think a very useful contribution to the class.
Thanks.
One final thing. So, as you know, I think the other contributor other than me to the course lecturing is Tom. He's going to give a lecture on statistics on manifolds, which might interest you anyway. He's doing that on the 7th of March.
Okay.
And I just fortuitous. I don't imagine, given his family obligations, that he's going to stay around. But on that Friday, the 8th, there's going to be many tens of demos at the department as part of the Brooks Memorial. And should you want to be in Chapel Hill, then you would enjoy those.
Yeah.
And the other.
Yeah, sorry. Unfortunately, Reyes is going to Spain that week, so I definitely cannot travel on my own with the kids. But,
sure. Anyway, those demos are not going to be on Zoom or anything, but the Saturday event where 5 panels will be telling various experience stories with Fred will be on Zoom, and should you be interested in that, then you can from home you could look at that. It's on a Saturday. Okay, thanks again, and I'll see you again about 3:25 on Zoom on next Tuesday.
All right, sounds great. Thanks, Steve.
Bye-bye.
Have a good evening.